Hello, everybody. I believe we have guests from Dallas, London, Berlin, and Bangalore joining us today. So, welcome to you all and for taking time out to join us for today's webinar. Selecting a reliable motion detecting technology for your application. My name is Clive Coldwell. I'm Group Editor of Electronics Weekly. And in this session, we're comparing different motion detecting technologies, reviewing the three most popular, and finally giving you a few tips on how to improve performance. We'll wrap up with a Q&A, and we're also running a poll today so we can see what design challenges you're facing. So to present and discuss the issues, we have two speakers. Up first is TI's Senior Systems Engineer Miro Oliecha, a well-known analog guru, author, and industry expert. Miro has spent 35 years in industry system design and semiconductors. Anthony Berthet is a field application support engineer with 20 years experience working with TI's Semiconductor Group. Welcome, gentlemen.
Thank you.
Quickly though, before we start, I've just got a few housekeeping items to cover. First of all, today's webinar will be available on demand after the live session, and it's accessible through the same link you're using now. However, we'd love to hear from you today, so if you have a question for any of our speakers, please feel free to send it through the example Ask a Question tab at the bottom of the page. We'll be holding a Q&A at the end of the session. And if we don't get to your question during today's webinar, we'll be sure to follow up afterwards. And finally, we'd like to encourage you to share today's webinar with your social networks. So without any further ado, let's kick things off. Over to you, Miro.
Hello, and good morning, good afternoon, good evening from Dallas. Today, as we said, we are going to talk about motion sensing and how to select a proper technology for your application. So let's start. What we are going to look today is going to be a motion detection technologies overview. So we will look a couple of different technologies that they are used. Then we are going to review three most popular sensing technology. Today, most popular sensing technology, motion sensing technology, will be PIR sensor. Then we will have optical time of flight, and then new coming mmWave sensor. After that, we will show you a couple of tips how to do the sensor fusion, how to combine these sensors, and improve performance of your system. The last part of the presentation will be left for the questions and answers. So let's start. So motion detection systems, they have different challenges. And when we say motion detection, that covers everything and kind of like nothing. Because if I don't go more specific in what you are looking to detect and where you are looking to detect and what your challenge is, you are not giving me any input, and it's very difficult to design the system just on generic motion detection. So first challenge that we have is ambient. So if we are having a motion detection that is outside, for example, video doorbell, then we want to detect the people. But unfortunately, we are going to detect the cars that they're passing. We are going to detect the trees, leaves of the trees that they're moving, reflection of the sun from the windows of the next door neighbor that when it's opening. Can be sunset, sunrise, direct sunlight. Also, another problem that can occur is the ambient temperature, ambient conditions. For example, if, like here in Dallas, the temperature goes very high, then the difference between body temperature and ambient temperature can be very small, and it can be very, very difficult to detect the motion. Now, performances are going to depend if you're using a single technology. For example, you're using a PIR sensor, or you're using a mmWave, or just a single camera maybe. Or you're using multi-technology and you are taking the best of both worlds. So how to do that, we will see on the next slide. Next one on the performances will be your algorithm. How that algorithm will perform, how a good algorithm will be to detect different scenarios. We published one of the TI designs with the two PIR sensors and wavelet transform, when we show that with a very good algorithm, you can detect if the person falls down, if there is a person rolling on the floor, if the child enters in the room, if there is a dog, if there is a fireplace running, if there is a sunset, and so on. So algorithms can go from very simple comparator type on-off to very complex with machine learning and artificial intelligence. And then naturally on the performance, it's your trade between the gain of the circuit and the noise of the circuit, because we know as we are gaining the signal, we are also gaining a noise. And so at some point, we are going to gain the noise and we are going to inject additional noise that it will be almost impossible to distinguish between the signal that we are looking for and the noise. Naturally, there are some special technology that we can implement, like a lock-in amplifier that can extract the signal out of the noise. So if the signal is maybe 10 times or 100 times smaller than the noise, we can still be able to extract that one using a different technology. So the first and most important thing is what is your scene? What you are trying to measure or detect. Are you trying to, do you have a good lighting? Do you have a narrow field of view? For example, I have here in my garage, I have a motion sensor, and that one is straightforward. When I enter in the garage, it triggers the light. When I exit the garage, it turns off, and no problems there. Or maybe you have a complex scene, outdoor, wide field of view, very difficult lighting, a lot of vegetations, and I can relate to that one perfectly with my outdoor camera or my video doorbell that is positioned and facing the south. So I have a sun basically during the whole day, and then I have a lot of cars passing in front of. There are some trees in front of that they're showing. So every couple of minutes I can get some of these annoying messages. Oh, there is a motion in front of your door. So yes, simple scene, very easy. Complex scene can be very difficult. So I have a little question here for you. What will be your biggest challenge that you are facing designing the motion detection? I will give you a couple of seconds to answer that one. So as I said, in my case, normally when I'm looking indoor, very easy. If I'm looking outdoor, start to be very complicated, especially during the summer when the temperatures are higher. Afternoon, if I'm facing west or south of the house. So there are several of these challenges, specifically targeting a false triggering. So false triggering, when we say false triggering, I always associate that one with the noise, and then the noise is directly associated with the gain. And so kind of like everything starts to be connected. So I hope that you have time to answer this question or maybe put your inputs. And so let's move on. So here is a table. And this table, we can always discuss if this table is accurate 100% or it's not accurate. This is best of our knowledge. And also it's more as a table that will make you think about different technologies. So depends how you apply the range, for example, can be different. You know, the fine motion can be different. It depends on your algorithm and so on. So here we look for different technologies. We have microsonic. So we have a sound. You know, we have ultrasonic, which is basically Doppler effect or time of flight, mostly time of flight. Microwave or millimeter wave, which will be using a Doppler and time of flight. Then we have PIR sensors, very popular. Heat change. So if there is a heat change, then PIR sensor will trigger. Then we have optical time of flight. Normally that will be in the infrared region. And the last one will be camera. So all of them, they have their pros and cons. Why we will use them? Some are measuring longitudinally better than laterally. Some of them, they have a wide field of view. Some of them, they have a very narrow. Some of them, they cost a lot. For example, if you're going to put a camera, that is going to cost a lot because the camera is very costly. But if you're just putting a PIR sensor, the cost is very low. Then we have another issue, which is power consumption. For example, PIR sensors are very low power. We made several TI designs that we can run PIR sensor with a wireless connection for 10 years on a coin cell battery. Why? Because the PIR sensor can run on microamps, and that's what we need if it's battery operated. Now we cannot say the same thing for the camera or for microwaves, which are requiring much more power. So we have also some advantages, disadvantages, and if we think about this table, it just gave us first snapshot of what we are facing as the choices. Now, another one is what will be our application. So we have external factors as dark or sunny, for example, bright light. And we know that the camera is very good during the day because we have a lot of light. We can see everything with the camera in perfect details. But once when the sun goes down and we have a night or pure dark, then the camera is starting to be useless. And so if in that case, we will need to combine camera, for example, with a PIR sensor, that during the night, PIR sensor will sense the motion and then will turn on the light. And only when the light is on, then we will be able to turn on the camera and analyze the background. So also there are other different environmental things like weather, fog, rain, snow. All of them can deeply impact technology that we are going to use, temperature, pressure. So for example, temperature, as I mentioned before, considering that PIR sensor is measuring temperature change, the higher the ambient temperature, the less change you have between the human body that you're trying to detect and the ambient, and more difficult starts to be. Now, another problem can be the surface that we are trying to detect. There can be transparent surfaces, plastic, glass. There can be a liquid in the surface, irregular shapes, light surfaces, dark surfaces, soft surfaces. For example, if you have ultrasonic and you have a very soft coat or a sweater, that ultrasonic Doppler effect or time of flight will be almost useless because it will not be able to bounce back from the soft target characteristics of the target. So next slide. So here is a very small summary of what we just said, and it will give you a better idea, how we are going to select different technologies for our motion detection application. So first thing is the time of flight. What is time of flight? Time of flight is when we are measuring time between emitted and reflected wave. So it's a sonar. We know everyone how the sonar on the boats work. We watch the movies and we see the ships chasing the submarines and having the pinging sound, ping, ping, and that's exactly what it is. We create a sound, the sound travels through the water, bounce back, and we measure the distance. Now, the same thing can be used by the policeman if you are overspeeding. Hope not. But, they will send the signal to your car. It will bounce back. They will measure the distance. They will do that a couple of times, and they will calculate your speed. Or they will use a Doppler effect. That's a different technology. So to use time of flight, we can use ultrasonic, because the same thing, that's your parking machine that in a car. If you have on a bumper, that's where you're using ultrasonic to measure the distance. You can use millimeter wave, or you can use infrared LEDs. Now, the motion, as I said, is calculated as the difference between distance and between two consecutive measurements. So we are measuring one distance, then we are measuring a second distance. Difference between these two distances will give us a motion. Opposite to time of flight is the Doppler effect. Doppler effect is working on a different principle, and that is it will change the frequency of the wave based on how fast you're approaching the source. And normally for that, that's called Doppler shift. And normally we use ultrasonic or millimeter wave for that one. And the third one is pyroelectric infrared sensors, where motion is detected as a change of heat. Now, what is important for this one? For time of flight and Doppler effect, the best, absolutely the best measurements you're going to have when you're approaching the source. In PIR sensor is opposite. The best results you are going to have when you are crossing the field. When you're approaching, then you're going to have a very bad signal. So basically, if we have a PIR sensor, only PIR sensor in a doorbell, and I'm approaching a doorbell, that will be the poor solution, because the PIR sensor will struggle to detect the motion in that moment. So let's go a little more in details on pyroelectric infrared sensor, or better known as PIR. So, okay, sorry, my. So what we are doing with PIR sensors, basically we're trying to measure the heat from the body, and there is a law that can directly relate the peak of the wavelength based on the temperature of the body. So for a temperature of 25, 27 degrees, 30 degrees centigrade, 300 degrees Kelvin, the peak radiation will be around 10 micrometers, and that is in the far infrared. So we cannot see that. Who can see it is PIR sensors, and for example, snakes, vipers, they can see infrared. Humans cannot see infrared. So what are typical specifications? Typical specifications that with PIR sensors can be used in a range of 10 to 60 meters. Now you will say, wow, 60 meters is long. Yes, but we can use it up to 60 meters. Field of view will be dependent on the optics that you apply there. And sometimes we have mirrors applied that we are concentrating the signal. Sometimes we have a wider field of view if we want to do in front of the house, or maybe in a conference room. Power is going to be in the microwatts, so very low power. Refresh rate is continuous because it's analog. Response time normally, because of the filters that they are applied there, is in a range of 0.1 seconds. And target characteristics will depend on ambient reflection and so on. So let's look more in details. PIR sensor normally has a sensor that, two sensors, that they are connected back to back, and then there is a JFET transistor that is going to amplify that signal. On the left side, you can see the visible light. Normally what we can see, you can see me in my orange shirt. I still have that same orange shirt today. And there is my coworker, David. He was working with me on the PIR sensors very extensively. On the bottom, you can see infrared image, the same image, but done with the infrared camera. And you can see that inside, you can perfectly detect the person with infrared. Now, at the same time, if we move that one outside, it will be very, very difficult to distinguish between the body and temperature and the ambient, because the temperature difference is very small. What is important here is that optics that we put Fresnel lens in front of the PIR sensor will make a different detection areas, and when we pass through that detection areas, we are going to have a signal that is going to be positive and negative. And very, very important thing for the future of our designs is that our DC level is going to be variable and huge. It's going to be between 0.2 and 1.5 volts. When our signal that we are looking a signal when we are 1 meter in front of the sensor, 1 foot, our signal maximum is going to be 3 millivolts peak to peak. So we are dealing with very small AC signal sitting on very high DC signal. So that all creates design that is normally today used, and that is going to be PIR sensor connected normally to double gain stage, where we have a bandpass filter. Bandpass filter will cut DC component out, will amplify AC component, and normally we'll have a bandpass between, let's say, 0.4 and maybe 10 hertz. Now, it depends on your application, depends on market that you're targeting, that can be adjusted. Some of the manufacturers, like Nicera, will implement bandpass filter and gain stages inside of their analog PIR sensor. And so now we have analog signal that is going out, and that signal is going to be triggered with upper threshold and lower threshold. What is good about this solution? It's very low cost. It is low cost and also very low power. What is bad about this one? It's a fixed gain, fixed frequency, and fixed threshold. That means that it's very difficult to avoid the false triggering. So if you go on ti.com, you will find a lot of literature regarding PIR sensor and motion sensors. We have a literature, tools, reference design. So here is the web page for you to look for. There is one of designs that we put there. You can look through the design, how it is done, what are criteria, how we select components, what are applications, and what are pros and cons of this application. So I'm not going to go more in details. If you are interested, just go on ti.com and look for TI Design 010027. What I would like to talk to you about today, which is very important, is a new concept. This is a flexible digital PIR sensor. And this sensor is done using a single chip, low power MSP430, where we are connecting analog PIR sensor, as we know, with all pros and cons. Pros are very low power, cons are signal is very small. We are connecting to the MSP430, and we are gaining that signal, and that signal is gained in real time. So what that means, I can change the gain of the signal in real time. So considering that we have a DC offset on the output signal, we are using internal DACs to offset that signal and cancel that offset and position our analog signal exactly in the middle of A to D converter signal. And after that, we are going to apply some algorithms inside of MSP430 as advanced filtering and so on. What is very important about this one is that in real time, I can change a gain of the signal. I can change the threshold of my triggering point, and I can change the frequency. So it's not only that I can have preset frequency response of the system, but I can change it in real time based on other parameters that I want. So in this particular case, when I'm not using oversampling, I'm using just pure 12-bit A to D converter. My full scale range is 2 millivolts, and that's adjustable. My dynamic range is plus minus 1 millivolt, and that again is adjustable. It can be much smaller. And my 1 LSB is 4.9 microvolts, and that's for the gain of 40 dB. Now, if I do some additional sampling, oversampling, I can easily push my LSB to 1 microvolt and look in a range that is very low. So very high distance, very low noise, and so on. We also have a wireless solution where the same thing is done using a CC13XX. So you can connect directly your PIR sensor to CC, and you can have a Bluetooth or wireless connection to your sensor. Here is now what you can see on these two solutions is that there's no capacitors. And these solutions are basically done because one day in a lab, I was doing the measurements. So here you can see the measurement. I have a bandpass filter and I have this noise. And every time that my laptop will turn on, the fan will turn on, or my scope, or someone will enter in the lab and slam the door, I will have a noise coming or signal coming from PIR sensor. And I was not able to understand what is happening. Capacitors are microphonics, and capacitors will pick up the noise around you. You slam the door, the truck passes in front of the house, and you will have a false triggering. And so here you can see without PIR sensor on the left side, there is a bandpass filter with the gain of 100 volts per volt, and you can see how much noise I have. When I remove the capacitors, my signal is completely flat. On the right side, you can see the capacitor-free signal, and that is the real signal of PIR sensor that is completely different from bandpass filter, because the bandpass filter, due to the capacitors that we are using them there, specifically on the high-pass filter, they are picking a lot of noise. So if you touch the board, if you knock on the board or do something, you will see that one. So we have a couple of launch pads done, so that actually it's a booster pack that is connecting directly to the launch pad, where you have a different PIR sensors, and you can connect them to the MSP430, or you can connect them to the CC components. And then there is also the GUI plugin module for the GUI composer, where you can see in real time on your screen different signals and how your system is performing. That will be all from me for now. Let's go to the time of flight.
Thank you, Miro. Okay, I'm going to share my slide now then. So I don't know if you can see my slide. Okay, let's start. So thanks for joining. It's Anthony speaking now, and I'm going to speak now about one of the technology that Miro mentioned, which is optical time of flight. So basically, Miro mentioned the time of flight. So
hi, Anthony,
this technology is
apologies,
time of
it's
flight.
Jade.
Yep.
The slides aren't showing. Could you just do that reshare? Apologies.
Oh, okay, sorry. Let me.
Slides are now on.
Share. So now it's shared. Do you see it? Can you see it? Hello?
I can, yes. Yeah.
Okay,
I can
good.
see the slides.
Now carry on. Then okay, thanks a lot. I'm putting it then full screen. Sorry for that. So Miro talked about time of flight, and it's time of flight, but with light as a medium. That's the only difference. Miro mentioned as well for PIR that it's working in something like a 10 micrometer wave. In our case, the light wave that we are going to use for that can go from 400 nanometer to 1000 nanometer. It's the typical range of the light we can use for the optical time of flight. I'm going to talk briefly about a couple of specifications that can be achieved by optical time of flight system. So typically, you can go from millimeter to several meters, even 10 of meters, but that's going to be very much system dependent. In terms of accuracy, you can reach millimeters as well, but again, it's going to be very much dependent on the environmental condition and as well on the key element of your system, so the LED emitting and the photodiode, as well on different conditions like ambient. Field of view is a very important factor in terms of the performance of the optical time of flight, because it's a strong contributor in performance like maximum range and accuracy. a general rule of thumb, the narrower the field of view is, the longer the range of the system. Then maybe to finish, I talk about a little bit about the targets that you want to sense. In fact, this particular optical time-of-flight technology I'm talking about is independent, will give measurement independent of the target color and reflectivity. The reason is that what we are measuring in this particular technology is not the amplitude, but the phase. So the distance measurement is going to be based on the phase that are going to be measured on the wave that is reflected back to the target. Also, the targets can be organic or inorganic. So it can be human, animals, plants, or it can be a wall or something else. So you can use multiple type of target with this type of optical time-of-flight technology. So the one I'm going to talk more in depth today is the TI chip called OPT3101. I'm going to highlight 3 key things here, which are the first, the 16-bit distance. So basically, we have a pretty good resolution, which can help you to get a very accurate range measurement. You can see something called a 15-meter unambiguous range. And this unambiguous range is linked to the fact that we are sending modulated light at a certain modulation frequency. And in fact, the period of this modulation frequency is going to give us the maximum range or maximum distance we can measure. Because since we measure phase, when you overlap of one period of phase, then you are at the end. So, and this one period overlapping gives you a maximum of 15-meter range to measure. The next point is sample rate can go up to 4 kilohertz, which means that you can really reliably detect moving target or even fast moving target. A very interesting feature of this device as well is a adaptive HDR. So it's an high dynamic range mechanism that's going to adapt the illumination, so change the power sent to the LED at runtime so that it prevents saturation. So in fact, somehow the amplitude of the signal will be measured, and when it reaches a certain threshold that's close to saturation, then it can decrease the illumination power so that you can keep measuring distance. One key of the OPT3101 is that it's very flexible in the way that you can choose the different element of the system. You can freely choose the emitter. So typically, the type of emitter could be a LED or laser diode, and as well the wavelength out of the spectrum that we shown at the beginning. Same for this receiver. You can have a wide choice of receiver that you can choose by yourself, and as well you can decide to use a receiver that has integrated lens or discrete lensing or even no lensing. Depending of the application and the use case, there are, and I will show one after, there is a way so that you don't need to use lenses. We have a couple of reference design, and I'm going to highlight one of them. You see that there are some links there, so you can get more information directly from the TI web if you want. I'm going to highlight one of those in the later slide. Okay, let's look at the block diagram of the architecture to understand a bit better how the system is working. So first, we have a kind of very accurate oscillator that will generate a modulated signal based on 10 megahertz that's going to drive LEDs, or emitters. You can have up to 3 LEDs in this case, and you can see the power and the granularity up to which one you can power them, and that's going to emit or modulated light wave. Then the light wave is going to hit the target and bounce back, and we have a kind of photodiode that's going to sense this LED, this light that's bounce back, and that's going to create some level of currents inside the photodiode. Now we have a very key element on chip here, which is ambient cancellation. So basically, we have the mechanism that is able to cancel part of the, or most of the, let's say, sunlight outside, up to 130 kilolux, which is going to mitigate for the ambient, let's say, part of the light.
Hi, Anthony. Apologies, your slides have come down. I can now just see you in full screen camera.
Sorry, I didn't get it. Do you see my slide or not?
No, I can see you at present.
Okay, all right. Let me share again. I don't know what happened.
Sometimes too much technology.
Okay. Okay, let me share again. I don't know what. Is it better?
Slides are back. We just need it in presentation mode. Thanks.
Okay, all right. Sorry for disruption. Fortunately, I ironed my shirt this morning, so. Okay, back to the slide. Okay, I'm go back where I stopped. So we were at the ambient cancellation. Is a key module to improve the incoming signal so that you don't get the ambient component. After that, we have the analog front end that's going to do most of the job. So in fact, the depth engine at the end is going to create free data, the phase, which we are going to use to process the distance. So it's going to be a simple calculation from the phase. It's a pretty much simple calculation to get the distance. Then we get the amplitude, which is going to be used for the HDR that I mentioned before. And then we have some ambient component as well that can go that can be used as output, and that will help to calibrate, for example, to calibrate the system. But typically, for the distance and the sensing of the proximity and distance, only the phase is used. Okay. We have an on-chip temperature sensor, and it's used to have a local temperature so that you can well calibrate your signal so that the results you get are independent from temperature. So it's another way to get a much better, let's say, precision on the measurement. Apart from that, on top, we have a I2C master interface that enables to connect, for example, an I2C EEPROM or another temperature sensor for better precision. And then on the right, it's all what's going to interface to the MCU via the I2C, where you have as well some GPIOs that enables you to save power, for example. Okay, I go to the next one. Okay, I'm going to show you a quick video. So we are going to see somebody passing by in front of a sensor. So it's based on 3 zones. Is horizontally moving, so you can see how it's transition from right to left. And then it's coming from the front. So you see how the zone reacts when somebody is coming in front of the sensor. So 3 zone means that 3 LEDs are emitting, and there is only 1 receiver. But because we emit in turn, you can in fact identify in which zone the human being is. So it's still coming from the front, and then you will see that it will pass by on the side. It's going to stop at some point. Okay, it's a bit further. I will wait. So yeah, he's coming here, he's passing by, and you see he's shaking his hand. So you see that the response of the system is pretty quick, because we could see the distance of the hand and as well right and left motion. Now it's coming quickly to the camera or to the sensor, and then passing back another time. So I'm going to give you a bit more information on the next slide. On the right, just to show you a picture on the right, it's a RLSLK robot, which is in fact following the end using this technology as well. So it's in the second video, but I'm going to skip it for now. I'm going to give you a bit more information, and now on the specific reference design that is about this technology. So the video that you saw before is in fact highlighting this particular TI design. Basically, you can detect from, let's say, 15 centimeter up to 1.6 meter with a pretty good accuracy within plus minus 10%. Then the sunlight is cancelled via the ambient cancellation, as we've seen. So it's worked pretty well as well outside. And we have tested this across different type of reflectivity. Just to show you some performance here. So first on the right, you see the 3 zone. It's what you saw on the video. Then the characteristic, so 120 degree field of view, what was used for the emitter, the photodiode used as a receiver, and the range. Now, in terms of performances, you see the type of precision that you get from this system. So you can see some measurement starting at 10 centimeter up to 1.5 meter, with different reflectivity going from 20% to 80%. So basically, it was a human model that was used with different clothing, reflecting more or less the light, in fact. And it's the type of accuracy that you can see you can get. So you see we are within 10% for the complete range of distance from 10 centimeter to 1.5 meter. At the bottom, you see as well some information about the power consumption. I'm not going to go too much into the details. You can find all the specification and all the measurement in the TI design on the web. Okay, I'm going to speed up because we are running out of time. So let me go to the next one. Okay, again here I will leave it to you since if you don't want or can't spend the time to do the whole development, we are a couple of solutions that might help you. As well as some partners that are providing ready-to-use solution with a different specification that can be used for home appliance, ATM kiosks, video doorbell, and so on. A couple of resources that you can use to get started. So to discover, we have a great system estimator tool that is just a simulator that enables you to quickly decide, okay, the technology is good for what I want or not. As well, intro to time of flight that will give you a lot of information about that. To evaluate, we have EVM plus very good Python-based tools that enables you to do automated testing, for example, and then as well a lot of collateral for the design when it goes to the PCB design, as well as calibration and writing the software. The time of flight team is helping or is answering directly on the E2E, which is a great place to get technical support while you are at any stage of the development, in fact. Okay. A little bit now about millimeter wave. I'm sorry, I have a bit to speed up since we need to keep a bit of time for the Q&A. So, okay, millimeter wave. So we TI has put out not so long time ago some millimeter wave sensor, and millimeter wave are very good as in terms of the fact that they provide high accuracy in terms of distance, speed, and angle. And this is independent of the environment. It can be dark outside, it can be some rain, dust. This is very reliable measurement depending independent of the environment condition. The only things I'm going to highlight on this particular slide is that it's a single chip solution. So you have multiple chips in a portfolio, but most of them are single chip solution, which is pretty unique. And we try to address both the automotive and industrial market. So automotive more in the 77 gigahertz range, industrial in the 64 or 60 gigahertz mmWave range. This slide is just to show you the type of application that can be supported through mmWave. So there are a lot of outdoor examples like street lighting, traffic monitoring, perimeter security, where it's important that to have a reliable system across different environment conditions. but it works as well great. It's great as well for indoor application, like in the factory automation, for robotics, or a forklifter that need to detect if people are passing by, as well in conference room where you can control the HVAC system depending on how people are in the conference room. So these are all type of application where mmWave is a good fit. Okay, just quickly go through the principle. So this is our single chip device, IWR6843. Basically, it's going to send a wave length. The part of the energy is going to be reflected back on the receive antenna, and what's going to go outside is a point cloud, which each point will have information on the distance, on the speed, and as well some information about the angle. So basically, you see a human on the left, and you see the point cloud corresponding on the right. And each point will have information on speed, range, so distance and angle. So this particular technology is based on frequency modulating continuous wave. So quickly, I'm going to show you what it means. Basically, we have a synthesizer that we are going to put out a specific wavelength, which is called a chirp, that is a continuous wave, so a kind of sinus there, that is frequency modulated, where so we are going to change the frequency over time. So this is the amplitude versus time on top, and you see the same wave at the bottom, which is frequency versus time this time. So basically, you start at 60 gigahertz, you increase very linearly the frequency up to 64 gigahertz. This gives you a bandwidth of 4 gigahertz out of a given period. That's a very linear slope. This is the red signal here. This red signal is going to bounce back, come on the receive antenna, which gives the blue signal. And basically, we have a mixer that is going to remove, or let's say give the continuous frequency difference between those two waves. Out of that, we are going to go through an ADC, digitalize it, and do some processing, F50 processing, to get the frequency, the specific frequency, that is the difference between the two transmit and receive. And this is a direct information about the distance. If you see the formula, you can see by knowing this frequency, the slope, you can get direct information about the distance, the range, basically. So this is just showing the principle about the range. I'm not going to show the principle for the velocity or for the angle, but it's just to give you a feeling on how it's working. Now, a given use case, let's say that you have a same radar hardware, and you want to support two different scenarios. One which is short distance, one is long distance. Is it possible? Yes, it's possible. Basically, all the secret is about choosing the right parameter for the chirp that we have seen before. Changing the chirp parameter enables you to support multiple type of scenario. I give you a bit more example now. So short distance, you see on the table, short distance, long distance. On top, the scene parameters, at the bottom, the chirp parameters. So you see by changing the chirp parameters, you can achieve some different performance in terms of range. So the maximum range in a particular use case, for example, for the short distance is 7 meters with a range resolution of 0.04, so 8 centimeter. What are those 8 centimeter range resolution? What does it mean? Basically, it's the distance between which you can still discriminate two objects. If you have two people in the scene, if they are spaced by 8 centimeters, it means that the radar is able to discriminate between the two. If they are closer than 8 centimeters, you cannot anymore. But as soon as they are 8 centimeters apart from each other, the radar has a chance to detect that there is two persons or more in the room. So that's what the range resolution is. Same for the velocity. For this particular scene, we are able to measure a velocity of 8 km per hour, and with the same concept for the velocity resolution. It's a minimal frequency between two objects that can still be sensed, basically. So we have that for the short distance and the long distance. So the same hardware can support both scenarios. You see it here using different chips. And the frame rate that you can achieve is 10 measurements per second. We have an extra long settings as well on the right using beamforming that can go up to 100 meters. But then you have to drop, for example, the rates measurement. So we have a good tool that enables you to assess if your use case can be supported by the radar. It's called the sensing estimator that can be used to, in fact, quickly see, I can make it with a radar or I cannot. Okay, I go quick on this one. It's just to say that, in fact, all the processing is done on chip, and we have accelerators that do that. We have even a DSP that can enable you to do more than giving you the distance, the speed, and the angle. It can even cluster the point together, track them, and classify, and for example, do some classification on object. Depending on the response, the power that is bounced back, you can decide if it's an animal or a human. And this classification can be done on the DSP as well. An important factor on the system is the dimension. It's in fact linked to antenna as well. Here we have one of our module, the ASK module. It's 55 by 55 millimeter. You see the black in the middle is a single chip solution, and then you have the antenna on top. 4 receive and 3 transmit antenna. Now we just have put out another device, which is the IWR6843 AOP, so antenna on package. What it means is we have put the antenna in the package. You don't need to design the antenna, it's on the package. So it's greatly reduce the complexity of the design and simplifies a lot the manufacturing process. So you can achieve very, very small system with that. Just put together a table that gives you interesting information about the antenna, because the antenna is an important factor to get the angle resolution. So azimuth and elevation, as well as reaching a given distance. So this is just a summary of antenna is important because it will provide precision on the angle of arrival as well as the distance. So you can go back to the slide later on if you need more information. Here, just to tell you that we have kind of information for different type of application. You just need to click on the black link and you will get the information to the point on the robotic, perimeter security, and so on. This is more detail on the design, which is about counting people in the conference room. This slide gives you the performance, range resolution, the area size that we support. In fact, it's a reference design where we provide the firmware, where you can quickly, in the firmware, enter the dimension of the area you want to sense. So these are...
Hey, Anthony.
Yes.
Mary speaking. We're kind of like running out of the time, so if you can
well, I'm wrapping up.
Jump to the fusion.
Yep.
Okay.
So performance will be on the link above. Skipping this one is just to show algorithm. Some collateral if you need more information, and let's go to the things quickly. So tips. So as you have seen, we have a lot of reference design. You can just take the design and build on top of it to improve the performance. That will be probably the easiest and the fastest way for you to make a product. So just improve the design that we make available. Second point is we have seen Miro show that PIR is good. I mean, it's low power, it's low cost, but it's not that great. So combining the technology together, like making some fusion, will improve a lot your system. In this particular case, it's a PIR plus a time of flight that enables you to sense further. So basically, combining technology is a great way to improve the performances. Then you can think about as well of bringing your end equipment to the next level. Here is just an example showing fusion of multiple sensors. What is typically done today in autonomous mobile robots, there are 100, let's say, or tens of sensors into the same product, because it's, in fact, cumulating sensor and technology can bring your product to the next level. That's basically the message. Yeah. We do a lot of other technologies. This is a table, so can you refer you to, because we talked only a couple of them today. One I just want to highlight in 2 seconds, in the proximity, we have a lot of interest due to the COVID-19 about sensing the proximity of fingers and hand. and not only touch interface to turn, for example, a touch pad into a proximity pad. So this Captivate technology is a great way to do that, in case it's what you are looking for. And we can go to a Q&A. Sorry for that. I had to rush over a little bit over the slides.
Thanks, Anthony. Questions are piling up, but we're not going to get through all of them, unfortunately. But Paul Massey, quickly from Saurian Electronics, is there a minimum distance that can be measured, and what are the limiting factors in that?
So let me comment on that one. We are talking probably on the optical measurement. The distance that we are measuring is based on a time of flight, and so the distance that you are measuring is the distance that the wave will travel from the source to the object and back. So if you're using the ultrasound, then that time will be much longer, and automatically the distance will be much higher. If you are going to use optical, then the distance can be much shorter because it will take much smaller time to go back. So because in you need to be shorter than the wavelength of the source. I don't know exact numbers, what is the minimum, but I'm assuming that there is physical limitations how close you can put your transceiver and your reflector. So that will be more on the physical position of these two sensors than anything else. If you're more interested into that, I can be back to you. Please let me know, and I will talk to the product line, and we will look exactly inside of the chip what are limitations. I'm expecting that it will be in range maybe of millimeter or something like that.
Yeah, similarly, Mark Madsen was what sets the minimum distance of 3101? What happens if the receiver is blocked close by?
Well, if the receiver is blocked, then it will not receive. And again, that comes to the, if I cover my ears, I cannot hear. So if I block the receiver, I'm not going to receive anything. But the question is probably related to how close we can put these two diodes, transceiver and receiver, and put a mechanical separation between them, and how close we can go to the object. So
one comment on that is for the time of flight, which is ultrasonic or optic, you will not see anything. The radar, the mmWave sensor, is able to go through plastic. You can have a plastic cover on the mmWave sensor, and you can still measure distance and things. So it's really choosing the right technology in this case. If you know there is a cover, then you have to choose, or there is a chance that it's going to be blocked by plastic or something, then you need to choose the right technology so that it can go through the obstacle.
Yeah, very good point. Thank you, Anthony.
Actually, whilst you're on mmWave, actually, Anthony, is there a way to access the raw data of the mmWave sensor to do some analysis?
So yes, so the sample data, the ADC data, can go out to a high-speed interface, and we have a board that connects to our development board that enables you to get the raw data, save it on a PC, and do some further analysis on MATLAB. For example, if you want to do some algorithm check or development. So that's completely possible with the boards that we have as development board.
Okay, and one last question is really, how can I determine the field of view for my application with time of flight in a practical way?
So if it's optical time of flight, do
you want me to comment on that one?
I can take an take an example. So
okay,
if it's about optical time of flight, first I take an example. This is what you want to see. So depending on how far you are and how big the object, you have a field of view. So first it depends on your target. Then the second is the emitter. You will have the emitter to send the light to hit the target. So the emitter you will choose need to have a certain field of view to emit the light. Then the receiver as well will have a matching field of view so that it can receive. From what I know, that what is important for the optical time of flight is that the bigger the field of view is, the more ambient light you will get and the less gain you will have. So you have to try to keep the field of view as small as possible for the optical time of flight. So it's one of the key things. So try to keep the field of view as small as possible, but it needs to match what you want, what target you want to see. So maybe you don't need to send the complete target, but just part of it. And then you have to match the component emitter and receiver so that they can emit, hear, and as well sense. I don't know if you want to comment further.
Okay, well, thank you, Anthony. Yeah, Miro, do you want to add a few things, or
yeah,
is that okay?
I saw the question about the capacitor-free design, how we do the filtering. All that is done internally to microcontroller, so it's very flexible and it's up to the end user. So that's my final comment.
Thank you. Well, I think we've run out of time, sadly, but there we are. But thank you to Miro and Anthony, and thank you for being with us today. If you haven't managed to get through with your questions, then rest assured, we'll get back to you. Thank you for joining us. Goodbye.
Thank you very much. Thanks for inviting us. Bye-bye.
Thank you. Bye.